that either you have not. Can you go back one? Forward. Can you go one forward, Liz? It's a dynamic slide. Go back. Liz? Click on forward. All right. So we also have unmeasured factors that, for whatever reason, you did not think about those confounders. You were running out of time or out of money to assess those confounding factors, and then your analytic portfolio is a little bit more limited. And one of the strategies is sensitivity analysis. And I will talk very briefly about sensitivity analysis, as they are somewhat relevant for the adjustment. So the simple sensitivity analysis, something that you see here, is you express the observed relative risk or the apparent relative risk as a function of the true relative risk times this term, what we call factor or confounding factor, where you see the prevalence of the confounder in the exposed times this factor, which is the relative risk minus 1, which is the relative risk between the confounder and the disease outcome, that is the strength of the confounder, divided by the prevalence of the confounding factor in the unexposed, and again with the same multiplied by the same strength of the confounder. So it's all about the imbalance of the confounder, prevalence of the confounder in the exposed over the prevalence of the confounder in the unexposed, multiplied by the strength of the confounder. Confounding is, as we saw in the triangle already beforehand, it's about the imbalance of confounders between treatment groups. That's the left side of this triangle. It's about the strength of the confounder. That is the independent association between the confounder and the outcome. That's the right side of the triangle that we had seen before. Okay, that's just expressed in this little formula, which is, we can see this in our textbooks from some 50, 60 years ago. It's nothing new, really. And then what you can do is you can simply turn this equation around and solve for the true relative risk. What should the true relative risk be given the observed relative risk? And then, again, of course, this term here, but what you can do is you can now express true relative risk as a function of what you observe and a bunch of assumptions. Now you make assumptions about the imbalance, the prevalence of the confounder, and about the strength of the confounder. And you assume that whatever is in this box here, in this parentheses, is unobserved. And you just change parameters in order to see how sensitive the relative risk estimate, the true relative risk, is towards assumptions of these parameters. Simple sensitivity analysis. Next slide, please. Like that, you see the assumed relative risk in this example is 2.0, and then when you vary the prevalence of the confounder in the exposed here between 0 and 1, the true risk is either going up in this parameter constellation or further down in this parameter constellation. An array of parameter estimates depending on your assumption of the missing confounder, which was term that we saw in this brackets beforehand. Okay, next slide. Again. Next. So that was sensitivity analysis in 2 slides. It's easy to perform using Excel. You can download it from our webpage. It's informative to explore the confounding where you have little prior knowledge. You can just play around with the parameters and see how it can play out. However, it really provides you an answer for a specific research question. It provides you an array of parameter estimates based on your assumption, which is it's a great tool to get some impression of the variability of your estimate. But you to be honest to yourself and say, look, what kind of parameters will I put into this, and what do I really learn from here? And also, this very simple algebraic derivation assumes that the the confounder is independent from the unmeasured confounder, right? That means that we assume that this association is zero. There's no association there. But in reality, of course, measured confounders like age, for example, are associated with unmeasured confounders like comorbidity, which goes along with age. So that means we are overestimating the bias caused by this unmeasured factor, because we're assuming that it's totally unrelated to the measured factor, which is rare. I mean, you can conceive that, but it's not very realistic. Anyways, we would be on the conservative side in that sense. We would overestimate the bias. Next slide. How can we then utilize this framework to adjust for residual confounding? We just use more informed assumptions and plug those into our sensitivity analysis. Can we base the inputs of our sensitivity analysis on empirical values that we either observe or that we get from the literature? What we could, for example, do, we have survey information where we might not have outcome information. It's a cross-sectional survey, but might have an estimate of the relationship between the exposure and the unmeasured factors that the factors that we observe in a survey, but that we don't observe in our main study, which is either claims data, electronic medical records, registries, whatever you have, some secondary data. And so, from the literature, if we are lucky, we will also be able to assess the association, the independent effect of the potential confounder on the outcome that we are interested in, which would be the side of the triangle. Okay, so we can kind of piece that together, this little puzzle, from different data sources. Next slide. Oh, right. So the example that we work through here is this good old example of COX-2 inhibitors versus non-selective NSAIDs and the risk for MI. And there are two example studies, one by Wayne Ray with a relative risk of 1.9 for high-dose rofecoxib, and one by Dan Solomon with a relative risk of 1.6 with high-dose rofe compared to non-selective NSAIDs, one in a Medicaid population, one in a Medicare population, average age 76 years old. Question is, can these associations be due to confounding by factors not observed in the claims data that gave rise to those two studies? Factors that come to mind are usually cardiovascular risk factors like BMI, over-the-counter aspirin use, smoking, education, etc. Okay. Next slide. Next, press one more. Okay. So, so the constellation that we have here is we have rofecoxib use, we have acute MI as the outcome of interest. We want to estimate the causal effect or relative risk of exposure on outcome. We have some unobserved confounders like smoking, aspirin, BMI. We have a bunch of measured confounders that are already adjusted in our main study. And we have those two parameters, right? The association between the exposure and the confounder, and the association between the confounder and the outcome. That ideally, if you click one more time. This association between the exposure and the confounder from a survey, and we get the association, the independent strength of the confounder from the medical literature, from meta-analyses, from original studies, from RCTs, whatever you have. Next slide. So we will work this through with an example using the Medicare Current Beneficiary Survey, which is a survey, all representative samples, slightly oversampled, the oldest old, of all the Medicare beneficiaries, 12,000 Medicare beneficiaries each year. It's a panel data set. You can be in the sample for up to 3 years. It's a face-to-face interview in the beneficiary's home. And has a 98% response rate, which is almost striking. They must threaten to take away your beneficiary status or something like that, that they get a response rate like that. among those who respond, the 98%, the data completeness is also striking with more than 95%, but that could be because there's actually an interviewer coming to your house, making sure that the data are complete. These data are available for very low costs. It's $1,000 per year. There's a lag time, however, of 2 to 3 years. It's hard to work with if you have newly marketed medical products. In our example, we're interested in these 5 factors as independent predictors of MI. That's the over-the-counter aspirin use, that's smoking, BMI, educational attainment, and income status. Factors, of course, you can come up with, they were not observed in the current beneficiary survey. I mean, the MCBS is not designed for this type of exercise explicitly. We're with the 1999 survey. One back, please. It's to 65 plus community sample, and we end up with almost 9,000 surveys. Next slide. So we're interested in the distribution of these particular confounders, obesity, for example, aspirin use, in different exposure groups, celecoxib, rofecoxib, and the non-selective NSAIDs. So let's look at any coxib inhibitors. Let's look at obesity. 20% are obese among coxib users, and 24% are obese among non-selective NSAID users, but only 17% are obese among the non-users that neither use coxibs nor non-selective NSAIDs. Now, what does it mean to us? Clearly, we have balance of obesity between the coxib and the non-selective NSAIDs, right? So we would not assume any confounding between contrast of NSAIDs versus coxibs. How we would compare coxibs versus the non-users, we would actually expect some bias because obesity is less prevalent in non-users. Go back once. Which could be once you're obese, your joints wear out faster, and you take these analgesics to reduce your pain. All right, that kind of makes sense. Let's look at let's say smoking status here. For smokers, coxibs, 55% of coxib users were former smokers, 51%, a higher proportion, 6 percentage points higher, of non-selective NSAID users were smokers. Okay, so there is some difference here. It does strike me as gigantic, but there is a difference. Slide. And as I had mentioned, the second part of this exercise is that you go in the literature in order to assess the independent effect of the 5 factors that you're interested in: obesity, aspirin, and so on. And we can probably talk at least a day for each of those factors. But you have to come down with some sort of best estimate. And our best estimate was that there's a 70% rate of risk reduction with regard to MI. A 70% increased risk of MI once you are obese, which is a BMI of 30 or more. And that is from a bunch of studies that are referenced down there. Aspirin use is 30% risk reduction. That is the trial, the physician's health study, of course. Smoking, about a 3-fold increase of MI. Education attainment, income status, high income status, low income status compared to high, doubles your risk of MI. And of course, we all understand that's not causal. That's just an indicator for other things that are going on in your life, most likely. But the best estimates, and of course, we can discuss whether they are correct or not. But this is how we go into this exercise. Slide. Now you just work through the algebra, and that's what the Excel spreadsheet is doing for you. So you have your literature estimate for obesity 1.7. The prevalence of the confounder, and that comes from the MCBS, is the 24% that we saw. The association between the confounder and the exposure group, and adjusted for age and sex here, is basically 1.0. Remember, it was 0.2 or 1.24, something like it. It was very similar between the coxibs and the non-selective NSAIDs. So it's a null association, really. We operate under the null in order to estimate the bias. Okay, the exposure of interest is 40% Cox abuse, and then the apparent relative risk would be 0.9, and the bias would be less than 1%, right? 0.1% bias, right? Not surprising at all. And why? Because the obesity is nicely balanced between the two treatment groups. So if no imbalance, there's no confounding. So let's go down this list here where there's a little bit more imbalance. So here's a bit more imbalance. 0.83. It's far away from the null, from a 1.0. That's educational attainment. And lo and behold, then we see with this literature, assuming a doubling in risk for MI, we see a bias of -2%. Okay? So it means we are not adjusting for this factor, we are underestimating the true effect by 2%. Okay? Next slide. And this is in the blue box that you see here, those are exactly the numbers that I just discussed with you. This tiny bias for obesity and this 2% bias for educational attainment. So the problem now is that we have 5 bias estimates that are very close to null. I don't think that anybody would seriously worry about these numbers, and we could actually stop this exercise. But if you want to continue here down this path, you will need some way to combine these bias estimates. And biases can cancel each other out. We know that very well. So one approach is this weighted average. You weight by the prevalence of the confounder, and you get this, -1%, and you get some sort of range, which is the sum of all negative biases and the sum of all positive biases, to get some sort of feel where you are, in which range, right? And of course, and we cannot estimate the precise bias effect because we don't know the joint bias distribution here, right? We assume independent, which they may or may not be. The other observation, of course, is that depending on what kind of contrast you look at, right, Coxib versus non-users, Coxib versus naproxen, Rofi versus naproxen, you get different bias estimates because the distributions will change. But overall, the largest bias, average bias that we observe is this -3%. So that claim set analysis would underestimate the effect by 3%, and few people get nervous about the 3% bias. Next slide. Next, good, yep. So apply that, the best estimate, the point estimate of Wayne Ray, the 1.9, will change to 2, and the 1.6 from Dan Solomon would change to a 1.7 if we incorporate in this external adjustment exercise the knowledge that we have gained in the survey and attribute it to our main study. When we talked about the literature review and assessing the independent effect of the confounder on the outcome, I was hinting already that it's we can come up with different estimates there. It's a shaky business really to come up with an estimate. And what you can do, of course, is you can do a sensitivity analysis for your sensitivity analysis. And for obesity, you remember we assessed a 1.7 relative risk between the confounder and the outcome, the independent effect of obesity on MI. Because these point estimates for bias, depending on the green one, is the contrast COX-2 versus naproxen, for example, right? I had picked a different cut point, so this vertical line would move either to the left or to the right, and the point with these lines, then with these curves, would be the corresponding bias estimate, depending on the assumption of the independent effect of this confounder. Next. That's all easily doable with this Excel spreadsheet that you can download. So you get the graphs as well, so it's fairly easy to handle. Next slide. So what are the limitations? It's limited to 5 confounders here because those were the factors that were observed in that survey. Enhanced thing, forget about that. We estimate the bias under the null. That is a problem. The further you go away with your point estimate from the null, the more the bias estimate is biased, but that's irrelevant because the farther you're away from the null, the more of an effect the Schneeweiss have and the less that can be affected by bias. So it's a non-issue, really. Next slide. What is much more important is really this here. We could not consider the joint distribution of the confounders, and even more so, we are limited to a binary world, right? The exposure binary, outcomes binary, and all the confounders have to be binary in order for the algebra to work out. Of course, we have to assume that our can you go back once? That the sample that we work with is representative for the main study. Next slide. So that's that it can address the joint distribution. It can handle more than just binary variables. In it, I'll published a method that were based on a logistic regression, but that could handle all sorts of metrics for the confounding variable. It could be binary, ordinal, normally distributed, continuous. It could handle only one covariate. We want to handle multiple unmeasured confounders. Next slide. So that gets to this what we call propensity score calibration. So the story is really how can we bundle a complex covariate vector into a single variable, and that triggered this idea because at the same time we were working on propensity scores, but that's exactly what a propensity score is doing, right? Potential confounders can be bundled into exposed propensity score into a single variable. And then what you can do in set survey, you estimate the propensity for treatment with all the measured confounders that you also observe in the main study. That is your base set of confounders. And then you estimate an additional propensity score with the measured confounders plus unmeasured confounders that are only available in substudy. Okay? And these unmeasured confounders within a propensity score can be seen as a measurement error problem. Now, so you have a propensity score with an error problem, the gold standard propensity score, right, where you have added that additional information, versus an error-prone propensity score where you know you're missing some information, right? And if you treat that as a non-differential measurement error problem, you can use this propensity score. It makes more sense when you look at the how the data structure looks like. So what we're used to is, let's say we have our main study, which is the claims data, right? And you have, in our example, we have the Medicare current beneficiary survey, which is what the measurement error people call a validation study. Yes. We have in the MCS you also get the claims data, so which is error-prone measurement of your propensity score, right? Contain all the information. But you can also have the MCBS, the claims data information plus the survey information. That would then be the gold standard. So here you see in the claims data you have the usual demographics, diagnostic information, prescription and visit information, plus the drug exposure. Against CVS claims you have the same. You also have this information here. You have smoking, aspirin, BI, education, and income, right? This is a richer propensity score, right? You estimate the propensity score of all variables below my purple arrow on this variable, on the treatment variable. This it becomes below this modeled on the treatment. Now, this is a reduced model, right, where you're missing all the survey data. The propensity score, which would be this here, an error-prone propensity score, which you would estimate here. You can estimate the relationship between those two propensity scores in order then to adjust this here, which is your main study. This MC is just a small subset of your beneficiaries. Next slide. Okay, let's do this in a more numeric way. You have the main study. Let's worry about the main study first. You have your outcome model. Right. right, with estimate your error-prone propensity score, right, and then you have your disease outcome model, which is the exposure plus your propensity score. So this is your propensity score model, D for this exposure and propensity score. With the error-prone propensity score, which is the propensity score that you observe really in your main study, right? What's unobserved is this model here that you don't observe in your main study, which is the probability of disease as a function of exposure and the gold standard propensity score, right? We can't have that in the main study. Next slide. That's why we go in the validation study, and there you estimate two propensity scores: one the error-prone and one the gold standard propensity score. Describe that. The gold standard is a richer propensity score with claims and interview data. Okay. Then you have a measured error model, which is simply, in this case, a linear regression of the gold standard propensity score as a function of the exposure and the error-prone propensity score. So it's a relationship between gold standard and error-prone propensity score, right? And the relationship is, parameterized in these lambdas: lambda 0, lambda e, and lambda x. Okay. There's note in here that the relationship is independent of the study outcome, which historically is the assumption which people often assumed is automatically fulfilled in a core study because the outcome comes later. This does not always have to be the case. But, that's a detail. Next slide, please. And then in step 3, you go back into your, can I go next slide, please? Yeah, one back. Next slide, please. You go back to the main study, where you then have the disease outcome here, and you have the beta star, which can be the corrected effect of the exposure, and the correction is displayed here. You see the lambdas are used for the correction, for the calibration, and the correction for the propensity score, which is also a function of the lambda here, right? But this, the red parameter, is the most critical parameter because that is now the corrected effect estimate. And the correction is simply here, parameterized with the lambdas. Okay. You can calculate the variance and all that stuff. So but the principle is that you estimate two propensity scores. You understand the relationship between a rich propensity score and a poor propensity score, the poor propensity score being your main study propensity score. Use that knowledge to correct your effect estimate in your main study. Next slide. So we went through this exercise here in a New Jersey Medicare population, 65 years and older, actually Medicaid and Medicare. They're interested in mortality, in 1-year mortality after NSAID exposure. Next slide. The Medicare current beneficiary survey is the same as we had used before. You see some C statistics for the error-prone propensity scores. The gold standard is higher, 0.66. You have more information now, right? So it makes sense. A better discrimination. Next slide. Assume, and this is a cohort of 100,000 people, and we assume that NSAID use in this population would not be associated with mortality. It does not prolong life, and it does not shorten life. The unadjusted effect estimate of NSAID mortality is 0.68, a 32% relative risk reduction. Bias because if you are close to death's door, you're probably not tinkering a lot with NSAIDs anymore. You're already on opioids or other pain medications, at least more likely, and that is triggering this effect estimate of this spurious protective effect of NSAIDs. It's a healthy user bias. And then do the outcome model adjustment for age and sex. The point estimate is moving up towards the null as expected, fully adjusted, a bunch of covariates. think so. It's moving further up towards the null, 0.80. But then, if you do a propensity score with the same variables, it doesn't do anymore, right? Propensity score is magic. Whatever information you put in the propensity score will be adjusted for, but not more than that. So 0.8, right? This 0.81. No big difference here. No difference essentially, right? But once you do the propensity score calibration adjustment, the point is it's moving up to 0.92, and there's a slightly different way to do that. You go even to 1.0, what we would have expected from based on our assumption that NSAIDs are not associated with mortality. Okay? So you see, you have a slide, please. Oh, yeah, next slide. There we go, yeah. So this correlation study, we see the same that we are doing quite well with propensity score calibration. Next slide. The beauty about propensity score calibration is that it's actually fairly easy to use. One understood the principle. What you do is you estimate really 3 propensity scores, and these are the proglogistics here. 1 in main study and 2 in your validation study, right? The error-prone and the gold standard. That information will be fed into a SAS macro for regression calibration. You can download that from Donna Spiegelman's webpage at the Harvard School of Public Health. And what you get is the unadjusted effect estimates, and then also the adjusted effect estimate. And adjusted means now for the regression calibration adjustment. And you're done. So it's really fairly easy. I mean, this is the entire code that you need for doing propensity score calibration. The same assumption as in the previous exercise holds. You need a validation sample that is representative for the main study, but you have the flexibility of going beyond a single confounder. You have the difference between the confounders are considered. The covariates can be of any scale, linear, or so great flexibility here. There are still assumptions like the surrogacy assumption, which is rarely validated, I would think, but theoretically you could think of something. And you have to assume that the propensity score, because you model the propensity score as a single variable, otherwise it doesn't really work with regression calibration. As a single variable, you a relationship between the propensity score and the outcome risk, which usually it's a good approximation. Right? Right. That is these are these approaches where you get information from a source that might be even outside of your study population. Of course, what you can do is within your study population, you can just go back to the original medical records or go back to interview patients and just collect more information. And that you want to do in an efficient way. That brings back, of course, again, this EP200 probably now, the sampling strategies within a cohort study. Now it becomes more costly to collect information, time-consuming, and you want to maximize the gain from the investment. And the 3 sampling strategies that we're most familiar with is, of course, the case control sampling, right, where you sample by outcome status. You identify the cases or a certain fraction of the cases, and then certain fraction of the outcomes, the sampling fractions, which is efficient because the power is largely driven, of course, by the exposed events. The case cohort sampling, where you sample by exposure status, and this is called the 2-stage sampling, where you sample by exposure and the outcome status, and then you have to reweight. Why don't we have now 4:45? Why don't we pause here or stop here? Because I think most of us know about case control sampling. Many will know about case cohort sampling and 2-stage sampling. It's important just to recognize that the sampling is simply by exposure and outcome, and you have to do some reweighting exercise. Keep in mind that crucial difference between this efficient sampling and the two approaches that I showed previously is that the efficient sampling, when you sample by the cases, by the outcome status, is specific to your application, right? It works, it's efficient, but it's specific to your application. And if you then have another outcome, you have to go again and sample again, right? While these other approaches will stay in the cohort mode, whatever information is already collected, you can reutilize and reutilize again and again in a less efficient way, but you don't have to go back to the source over and over again. There's this trade-off. And depending on what you're doing, one approach might be better than the other. All right. That was a long monologue, and I want to open this now for questions and comments.
The last slide you have about efficient sampling and the connection to this slide to propensity calibration is not related, right? You are not talking about propensity score with efficient sampling. This slide talks about the independent approaches of...
Yeah, it's a different approach. That's right.
Okay, all right.
Could you give an example just of two-stage sampling within a cohort? I mean, what do you actually do? I mean,
But what you do is let's say you're operating in a claims data set. You can identify the exposure and you can identify the outcome fairly cheaply. Let's say there's an and there's the COX-SIP exposure, right? That doesn't cost you much money, right? Instead of just sampling by the case control status, you can now sample patients by case control status and by exposure status. You can kind of have a 2x2 table, and in each box of the 2x2 table, you will sample the same number of patients, let's say 50 in each box, which comes up to 400 patients at the end. Sorry, 200 patients. And only for those 200 patients, you go back to the original medical records or you interview these patients, gain more information, right? Very detailed information. But then because of your forced sampling strategy, you have to re-weight that knowledge in order to apply it to the main study. I think you will be able to download the presentation later from the WebEx, and there is a bunch of literature that I provide on that and have some more slides on two-stage sampling. Any questions?
This is Bill. We were kind of having side discussions about this. My question, I guess, is how similar does the calibration population need to be to sort of your more limited data population? We're getting into the discussion sort of like the indirect comparisons issue. If the control group is different between them, you could get into trouble. And I was just wondering if there's anything you could say about, if you're going to a different cohort for your calibration data, how much this is going to be an issue.
Right. Really, it would be now just a random sample, right? If in our exercise, most likely it was not a random sample because the Medicare beneficiaries that we worked with were from Jersey, and they were a little bit older than the average Medicare beneficiary. So what there is to make them more similar, because you know some of the characteristics. But even if you don't do that, what has to be representative is not exactly the population composition. What has to be representative is the calibration factor, right? It's a question, is relationship between the error-prone and the gold standard propensity score the same in that population as it would be in your population, which have the data in your own population? Removed a little bit from the exact population characteristics. So I would think that the representative assumption, it's still there, but it's a bit more relaxed because we are interested in the calibration factor. We estimate the calibration factor, not other specific population metrics. But that's the consideration. We have never really studied that any further.
Yeah, I was trying to think how you would. Just, the temptation is sometimes there to go get the more detailed data from some other data set rather than, if you don't have a sample of your own. So
what we do, so that's a study that we're doing right now. Jen Polinsky is leading that in our shop, where we do have from the CMS chronic disease data warehouse, we do have these ABD data in a cohort of a exposure, and for some of the patients, we strike gold, and they are linked to an MCBS. They participated in the MCBS, and we have the MCBS information for those patients. We have kind of what we would call an internal validation study that is really out of our cohort. At the same time, we bought the CDs for the MCBS for the entire nation, right, which would be our external control group. And now we can compare in this setting to what extent the calibration factor is different from the internal validation study compared to the external validation study.
Yeah. Well, that'll be interesting to see.
Indeed.
To point out, Curtis, so if you have your gold standard propensity score measured within a subsample of your main population, are you better off using propensity score calibration, or is that more of a multiple imputation problem then?
Well, but the assumptions are different, right? I mean, the short answer is no, I don't know. I don't know, but we can now speculate which approach is more robust. Degradation approaches, they're tricky. They can be highly effective, but essentially you're calibrating something, right? And the smaller the population is that you use to estimate, if you're slightly off, right, with your calibration estimation, right, you're calibrating that to the entire population. You might be, off quite a bit at the end. And I'm not sure how sensitive the imputation strategy would be. But in a situation where the proportion of patients that have the additional information is very small compared to the entire population. So we are talking maybe 3% of the population has MCBS available, right? And you're trying to impute then for 97%. That's usually not what you mean by imputation. Imputation, when you talk to experts, they usually want to see that the information is available at least in the majority. You're imputing in the minority of your population. So
then that propensity calibration is going to perhaps even worsen, if not help you, if you have a small subsample of your cohort, which you have the gold standard propensity score and those confounders that you needed that were extra. If you have sort of large ratio, most people don't have extra.
But it depends on how well you're doing with estimating the calibration factor. If you estimate it right, you're all set. You're good to go, and you will estimate it validly. And how you do with estimating your calibration factor depends on how representative your sample is, and depends on how valid your measurement error model is. Is the linear regression a good approximation, or do you need a nonlinear regression model, right? Okay. How about disease risk scores? Do you think it is a good way to controlling for confounders? Oh yes, sure. I mean, in a generic way, yes, that's fine. It's like a propensity score. Propensity score are a bit more useful if you have few outcomes but a large number of confounders that you're worried about. Disease risk score in the calibration approach usually is not so handy because in the small subsets that you have, the surveys like the MCBS, for example, is cross-sectional. So it's panel, but yeah, it's a pain in the neck really if you do longitudinal studies in MCBS. But even if you would do a longitudinal study, in order to assess the disease risk, that's what you have to do, right? You will have very few outcomes. It's a very small sample. Therefore, usually it's not that helpful. That's why we never even started to do a risk score calibration approach, which in theory is kind of very similar to the propensity score calibration, but it doesn't make any sense in most of the settings that we were concerned with. But as same, you condense a large covariate vector into a single variable, right? By looking at the outcomes, at the risk for the disease, while we're looking at the risk for exposure, or the chance, or the propensity score, the propensity for exposure. Questions?
So this is John Seeger. I had a thought that was my mind as you were going through the presentation, and that was about some times with like in insurance claims data, you have a lot more data than the time frame of your study, and I've seen the temptation to treat data in the same framework that you're talking about here of being like extra data collection. That is, they'll use you have a claim for smoking during follow-up or even during the after the complete set of the study time frame as an indication that they should turn on that variable for the subset of people who have that. I think in the context of your discussion about the immortal person time, sort of where that might be usable and where it's problematic.
Well, that's not all about the sequence of on timing, right? And clearly, we should not look in the future in order to determine our confounder status. However, there might be exceptions to that, right? If the variable that you're interested in is totally independent of the outcome that you're studying, so it will not be influenced by what's going on during follow-up, then it might be okay. So if you think of genetic makeup or things like that, I mean, that does not change with time. So we're talking really about genes, not expression of genes, just genes. They should change over time. And then, I don't care whether you do this before the exposure, after the exposure, after the outcome. It should not change. With all the factors, you usually can come up with stories why it's a problem. But that's a tentative problem, not so much a external assessment.
And there was an example we have of a study that you and I did on aprotenin, where we did sort of the cohort sampling to get some additional clinical data on. So we went to medical record, got some additional clinical data on patients who received coronary bypass grafting and some of the features of them. We only had it for a single institution within a cohort study that had multiple institutions, and what we're thinking back to is you could run into a very similar problem of temporality with this kind of sampling, because the issue might be, well, was it the same cabbage surgery that they had but we'll use them in the main study, so that the temporality questions can be more complicated than they might appear.
You're absolutely right. If you look at medical records, and sometimes not even recorded when certain entries make it into the chart, right? They're just there in one of those fields. You don't know when it was assessed. Was it assessed before your exposure, before outcome, or after? That is something that once you go into the field work, into the woods, then these are issues that come up very much so. Any more questions, please send an email to me. Feel free to send it. You will see the PowerPoint slides on the WebEx, and any of its articles. We might post some of these articles as well. And if you browse down the slide presentation, at the end you see 2 slides full of literature references that may or may not be of interest. So thanks for your attention, and In a month's time, there is multi-structural models with Miguel Hernan, and then in May we have the propensity scores by John Seeger. All right, here, selected readings. There we go. You will find them in the slides. Thanks, everybody.
Thank you.
Thanks.